Good morning, students. I guess, like I say, I always start the morning with the weather report, and we're back again, still in our springtime weather. So I haven't even looked at the forecast for um, the for spring break, and so I'm not going to do it. I'm not gonna do it because I'm just gonna keep my fingers crossed that we won't have rain every day like we normally do. But uh, that's always like I say, it's a plus to have time off, but I enjoy the nice Texas weather when we have time to get out in it. Now, I've gone ahead and posted the results for the test. Again, you know that their solutions on Blackboard. For the most part, I was very pleased. I saw improvement. I still do see some evidence of using computer algebra systems, and I know that's something that you're going to have to work on. I'm very lenient with that. Um, I do, however, notice when there's an example that everyone works and they seem to have the same response, for the problem, which is incorrect. I do want to salute those of you that are, and which is pretty much everybody, making the effort to do good work, to submit your test work. Uh, there is one particular example. Let me share with you. If you go to Blackboard with test solutions, here are the test solutions that I post. They have the same for the first test, and I found good work. Um, the one interesting problem was this one, where you had the exponential, where all you had to do was adjust it with a conjugate type method, or not even a conjugate, but just an algebraic manipulation to make it table ready. And I got some interesting results on that, which seemed to be in several papers identically. And so my again, I will practice leniency as you stop using these websites. Again, it does take a while to get into a process of having integrity in your work, and I will give you time to do that. Seven was an interesting problem too. Some of you used the Weierstrass substitution, which I had not even taught at the time. And again, this was just a conjugate method like I teach you in class. Um, I did have one paper that actually used the integration by parts method here. Most of you use substitution, which is fine. I mean, miscellaneous. It's a valid technique, but I was very happy to see one student who used what I had presented in class. And then, of course, the hard part was just reducing it to a form that was nice. Okay. 10, I saw good work. Again, that's an even function that, again, nice properties that you'll use when you do Fourier analysis. In number, the secant, these are all randomized, but in the secant cubed, remember I said if we do a problem and derive a formula in class, you can use it. So I wrote derived integral formula. So you can use these formulas. You don't have to start from scratch. I don't want you to do that, because if I prove a formula in class, you are more than welcome to use it and not have to start over. But I appreciate your work. Just remember that again, the pursuit of excellence takes plenty of hard work and determination and consistency. So I appreciate that. Now, there was one other thing that I wanted to share. Let's see, let me find it. If we go back to courses here, this is what I was talking about, the SJC Code of Academic Integrity and Honesty. Integrity is one of the core values of San Jacinto College. As such, students are expected to exhibit honesty, integrity, and high standards, and freedom from lies and fraud. Fraud is misrepresentation, ladies and gentlemen, and that is a horrendous offense. Okay. Fraud is misrepresentation of work, and it can come in many different forms. Personal integrity is important in all aspects of life, and students must conduct themselves in an ethical manner, both in and out of the classroom. Incidents of academic dishonesty will not be tolerated, and students guilty of such are subject to disciplinary consequences. I am being lenient. So For the next test, the fourth test, and the final exam, if I see any evidence of the use of a computer algebra system, that will be academic dishonesty, and I will prosecute it. Ladies and gentlemen, I mean what I say. I will help you learn, but you have to put in the time and you have to follow the code of conduct of our school. It is a stringent one. This academic philosophy is exactly the philosophy of my undergraduate school, the University of North Carolina, and also Texas A&M in College Station. Again, you can get all the help you need, but you must present your work in an honest way. So please keep that in mind as you do work for anything. I want the best for you, but I want you to be able to succeed. That is, when you get to the university, I want you to have a plan of integrity that gets you to that finish line. Okay, so now let's go ahead and do the next topic. With what we've done so far, we've talked about L'Hopital's rule and using the integral tables, specifically the Weierstrass substitution, which allowed us to conquer, so to speak, rational functions of sines and cosines when a conjugate technique or some other simpler technique really wasn't available to us. And we found that, you know, it was fairly reasonable, but algebraically busy, but certainly no more difficult than what we have been doing. So what we want to do today, because a lot of you, like I say, as you venture into your engineering math, you're going to use transform methods. And transforms are integral objects that make functions nicer. Okay, when we want to transform a function, we want to remove corners, we want to remove discontinuities, we want to make the functions nice and smooth, and that allows us to operate on something with calculus and then reverse the process, so we can solve a problem in a nicer situation and then reverse it for the solution. Now, that's what you're going to do when you do the Laplace transform method. I'm going to say a little bit about that in the Fourier transform, just to give you examples of this. But in order to do that, we need to talk about some improper integrals. Now, what makes an integral improper? That seems kind of crazy. Aren't integrals just good things? When we say improper, we're not calling them bad. We're just saying that they are not the standard integral. So, for instance, our first example will be infinite limit of integration. Infinite limit of integration. Now, one interesting example, this is one we're actually going to finish off by induction, but I'm going to use n equal 1 in this case. So we're going to consider the following example. It looks like this. The lower limit is 0, but the upper limit is infinity, x e to the minus x. So you're thinking this would be a good candidate for integration by parts. Now, the reason we do this, the reason we actually do this, and also I just want to say one more thing. I'm not going to call you out individually, but you all, 3 of you did some exceptional work on this test, and you know who you are. I just want to say, please keep up the good work, everybody. Just keep working. It means a great deal to me that the work we do will change how you look at mathematics. It will change you as you perceive physics and engineering, just like this problem here. And that is rewarding. That just gives you that sense of, wow, look what I'm doing. I'm moving to that goal of being able to change the world. Maybe some of you will be the future Bill Gates. You'll come up with some new technology, mathematical technology, and change the world. So that can happen too. Now, sorry, I digress. Now, when you look at this, we're thinking, okay, how do we treat something like this? How do we make it proper? How do we make it proper? Well, the thing is that we just do a sleight of hand. So when you have a limit of integration that's infinite, and it could be negative infinity down here if you wanted, we just do a change of notation. And here's what we do. And I like to introduce this through examples instead of going through definitions that just make your head spin. We'll just say the limit as b approaches infinity, 0 to b, x e to the minus x dx. Now, when you look at this and you just cover this part up, that's a proper integral. That's what we're accustomed to. But in order to make sense of the infinite limit of integration, we just say, compute this integral like you normally do, and then pass to the limit. So the improper integral with an infinite limit of integration is defined this way. So we write it as a limit, but treat this part as we normally have. So we don't jump the gun, so to speak. We just kind of drag this along. And once we get this to a finished form, just like we're in calculus 1, we take the limit. So again, now we rewrite the improper integral as a limit with a proper argument, okay? So now when you look at this part, and this is very simple. I always say things are very simple. They're simple when you know what you're doing, right? And I'm gonna help you understand what you're doing with these problems. The first thing we wanna do here is say, well, let's just do integration by parts, and we can use our method tabulation as we always do, but this x differentiates to 0. So let's just go ahead and write that out. And we'll do it in the informal setting. So we start with x as the object to differentiate, and e to the negative x as the object to integrate. Again, very easy in both cases. So we get a 1, and then of course we get the negative e to the negative x. We always like integrating e to the x. That's always a joy. And then of course, one more step, differentiating the 0, or excuse me, the 1 to 0, and one more application, we'll get negative e to the x, made negative is e to the negative x. Now, of course, we've exhausted the integration by parts with 2 applications. Here's the new u and dv applied again, and then we simply connect. I had students that go to Texas Tech, and they take an honors differential equations class as a junior, and then they call me back or send me emails saying this was so helpful when they did Laplace transform. Because at first they don't understand it, and then it sinks in, and they're like, "Yay, this is easy! I can remember this now." Okay, so here is our antiderivative, which we can now place into here and use the fundamental theorem of calculus. So now we have the limit as b approaches infinity, and we'll just go ahead and substitute. So we have x and a negative e to the negative x. So we have negative x. Now what I'm going to do, I'm just going to put the e to the negative x downstairs as e to the x. So we can think of L'Hopital. Okay, that's why we did L'Hopital, because now we're going to need L'Hopital, and you know that we'll be able to compute that based on what we did last lecture. And then for this one, notice this is again going to be a minus, so we're going to have minus 1 over e to the x, and I'll go ahead and move this downstairs like this. And then, of course, we're evaluating from 0 to b, okay? Now, just like, again, we've still got this limit out here, but now we just apply the second part of the fundamental theorem of calculus, remembering that in the final analysis, we'll have to take the limit. So we'll use a bracket. We apply the b, that is, we replace x with b. So we have negative b over e to the b. And of course, you could have factored this negative probably. Let's just go ahead and do that. This is just all these negatives, you know, that's like, my goodness, let's just get rid of them. Let's just go ahead and factor this negative out here. That way it doesn't get in the way. So this will just be equal, and we'll just have the -1 out here. Just use the linearity of the limit, okay? Then we'll have, in this case, plus 1 over e to the b, then minus, now we'll replace x with 0, and of course that zeroes out this term, plus, we replace x with 0, and this will just be, in this case, 1 over e to the 0, which again will just be 1. So now when we look at this, we can say, okay, we're good to go. Let's go ahead and simplify this just a little bit more. So we have -1 limit as b approaches infinity. So we've got b over e to the b plus 1 over e to the b. And then, of course, here we just have a -1. Now, this is where we can use our calculus 1. Notice this limit is clearly 0. That is, as b approaches infinity, we have 1 divided by infinity, which converges to 0 from our calculus 1 techniques. And then, of course, this we can use L'Hopital. Again, if we apply L'Hopital, we have infinity over infinity. We can take the derivative upstairs and downstairs. So let's do that. So we'll have L'Hopital to apply to this one. We've got the -1. So this will be, and of course, since I'm going to go ahead and apply the L'Hopital, let me not leave out the limiting process. I don't want to skip that step. That'll make it a little bit difficult. So let me just go ahead and put this in here. So when we differentiate the b relative to b, we just get 1. And then, of course, e to the b, like e to the x, is e to the b. And then we have plus 1 over e to the b minus 1. So now when you look at this, both of these, now we basically transform this into this. And L'Hopital says that if this has a limit, it's the same as this one. So of course, now in the limit, both of these are 0, because again, 1 over an infinitely large real number converges to 0. And of course, this is just -1. So in the limit, we get -1, 0 plus 0 minus 1, or -1 times -1, which is +1. Now, here's what we need to be able to glean from this. Now, I will say this, with the L'Hopital's rule, I want you to apply it, but if you're doing, like, if, for instance, if you had, say you had, ladies and gentlemen, b to the 3rd power over e to the b, you're thinking, well, I'm going to have to apply the L'Hopital's rule 3 times to make the b cubed into what, 3 factorial. Okay, so I won't say, okay, you need to show me all of those iterations. You could do L'Hopital's rule and just say that and do a little sidebar to say that this limit will be 0. Again, there will be some flexibility in how you apply the L'Hopital's theorem, because again, when we think about rates of growth, exponentials are always going to grow quicker than the standard polynomial because of L'Hopital's rule. So the main thing here is that we notice this we understand from Cal 1. This now we understand from Calculus 2 via L'Hopital. So if you want to do a little sidebar when you have a larger power here, that is certainly fine, and then indicate the use of L'Hopital's rule. That is more than sufficient detail to do this problem. Now, what does this mean? Okay, when we have an improper integral of this nature, that is, we are taking a limit and we're saying that this limit exists. So when we have an improper integral that exists, we say it converges. So we say improper integral improper integral converges. So when we take limits and we in Cal 1 and we get a real number, we basically see that that limiting process exists. That is, the function converges to some number as, say, x approaches 1 or x approaches infinity or something like that. So the idea is we want to be able to think about the improper integrals the same way that we're going to think about infinite series. So we may not always know, for instance, when we're checking whether or not an improper integral converges or diverges, we may compare it to some other improper integral that we know converges. And by comparison, we would be able to determine whether or not the given integral converges. So what we're finding here is kind of not the case usually. That is, we're actually finding the actual value of the integral, which is something we love to be able to do. But when we do infinite series, many times the best we can do is determine convergence and then give a really nice estimate of the actual value. So again, the idea here is think calculus 1. When we have an infinite limit of integration, we rewrite it as a limit problem where we consider the proper integral as we've done all through here. And once we have basically simplified to this point, we now pass to the limit. So we just drag the limit along with us, like doing a derivative symbol. And of course, any properties of the limit we can utilize as we move through here. Like I said, let's get rid of all of these negatives. So I factored the negative here. That is still in play. You can still use the properties, the theoretical properties of the limit. So again, in this case, we would say that this particular improper integral converges. Now, it's kind of like solving equations. You either get a solution or you don't. And when I teach this, I want to make sure that we do enough examples where the integrals actually converge. If you do a limit and it's just infinity, then that's the answer. And you say it diverges. So we'll just say if the limit does not exist, then the improper integral diverges. So we have two ways of classifying this type of improper integral. Either the limit exists, converges, or the limit does not exist, diverges. Okay, so these will be terms that we will use often as we move into the next chapter. Now, I was going to do a more elaborate induction argument, but I'm going to hold off on that because, again, I want to make sure that you get the computational technique down. There is one other type of improper integral that I'm going to introduce, but now what I want to do is do an example that has infinite limits below and above. So the key here is classifying the improper integral and then writing it in terms of operations that we already understand. So here's another example. And of course, you see that with the improper integral, we get to use our techniques of integration, just like we've been doing. And then so we also get to use our new limiting strategy, which is L'Hopital's rule, when we need it. We don't always need it, okay? So if you don't have to use it, then even better, right? So now, when we look at this particular problem, and let me get some focus here. When we look at this problem, we know that it does vary from the last one. Now, you might be thinking, how do we figure out how to break this up? Obviously, it's going to be two pieces, and this is where you have flexibility. For instance, here we could just take a number, a finite number, and have that be like the bench point. That is, we can go from negative infinity to that finite number for one integral, and then the finite number to infinity for the other. So just because we're lazy and we don't want to make things complicated, we can just use zero. So what we can do now is say, okay, this will be the limit. Well, let's not even do that yet. Let's just wait off. Let's just say we're going to break it up into two pieces. This is called the Cauchy principal value. So we're going to say negative infinity to 0 of 4, 16 plus x squared dx, plus basically using a technique that you learn in Calculus 1. If you had to prove this in Cal 1, it was tough. It usually is left out. I prove it, but it's not a lot of fun. You have to work a lot with the partitions. So we always think of breaking up an interval of integration. So we're thinking negative infinity to infinity can just be written as negative infinity to 0 and then 0 to infinity with two integrals. And now we can apply the definition of improper integral to this one and use any letters you like. Of course, don't use any letters that are already in the integrand. Of course, that would be difficult. So we'll pick maybe an A and a B. So now we have the limit as A approaches negative infinity, and we'll say A to 0, 4. And while we're at it, we'll just write this as 4 squared because this is going to be arctan. We're like, kind of stuck with that. And we're happy to see it's something that we can do readily. Then we can say the limit as B approaches infinity of 0 to B, 4, and then of course 4 squared plus x squared dx. So how do you deal with infinity below and above? You break it up and you have the choice of using any finite intermediary. And usually in probability theory, statistics, real analysis, 0 is good. Now, the one thing that we've noticed about this particular integrand is that it is defined for all real numbers. You're thinking the other type of improper integral would be where we would have an infinite discontinuity in the interval of integration. And so we don't even have to deal with that. And of course, the worst case would be where you have the infinite limit and the infinite discontinuity. So you've got two things to have to negotiate that are different. So at this point, we compute, and then pass to the limit. So now, of course, this is the arctan, so we're good with that. Just notice we have A equals 4, and we have, in this course, U is equal to X. So du equals dx. So now when we think about this, the 4 just kind of hangs out. We don't really worry about it. It's just going to absorb the 1 over A, but no big deal. So this will be the limit as A approaches negative infinity. So the 4 is already up there. So we have the 4, 1 over A, which is 1 over 4, arc tangent of X over 4. And we evaluate from A to 0. Do the same for the next, plus limit as B approaches infinity. Again, we have the same antiderivative, 4 over 4, arc tangent, X over 4. Now, if you want, we can double bracket and then the line 0 to B. So when we look at this, again, this would be a nice integral for the very first week of class. All right, we do the inverse trig forms. And now these are very simple. We can apply the limiting process once we apply the second fundamental theorem of calculus. So this will equal the limit as a approaches negative infinity. Of course, we will apply 0. So we have inverse tangent of 0 minus inverse tangent of a over 4. Again, replace x with a. Of course, the x replaced with 0 just gives us 0 over 4, which is 0. Then plus the limit as b approaches infinity. Apply the fundamental theorem of calculus, part 2, inverse tangent of b over 4 minus inverse tangent. Of course, we substitute 0 and we just get 0. So now, of course, all of this simplifies. We know inverse tangent of 0 is 0, so we can do one more simplification. So we have negative inverse tangent of a over 4. And of course, we'll have to remember the actual range of the inverse tangent, which we know from our study of pre-cal, plus the limit as b approaches infinity. Again, this is 0, so we have inverse tangent of b over 4. Now again, we're thinking, okay, well, the inverse tangent is bounded above by pi over 2 and bounded below by negative pi over 2. So again, here we can factor the negative. So this will be the negative. A is approaching negative infinity, so the lower bound is negative pi over 2. Now B is approaching infinity. The upper bound is pi over 2, so we get plus pi over 2, just using the range of the inverse tangent function. So of course, this will give us pi over 2 plus pi over 2, which is pi. So now when you look at this particular improper integral, I like to do ones that converge so you can build your confidence. So in this case, we say the improper integral converges. Again, just like I said before, the integral transforms that you will use in differential equations, namely the Laplace transform, which is related to the Fourier transform, are these types of improper integrals. The Laplace goes from 0 to infinity. The Fourier goes from negative infinity to infinity. So again, integral transforms mimic the probability distribution functions in probability theory, because when you have a distribution function, you want it to have certain characteristics based upon the integration of it. And so again, these improper integrals, at least this form, do occur quite often in mathematics and engineering. And so you will encounter this type of improper integral more often. Usually the other ones students will mow over, and we get lucky that, okay, we get the answer, just because things worked out in the wash. But as you do some research and you look at some other types of mathematics, you will find that these transform methods exploit this type of integral. Again, the transform method is ingenious. Like I said before, it takes an object, a function, and makes it nicer so you can operate on it and then invert the transform. So you have the forward and the backward, just like you have a function and its inverse. It's the same idea at work. Okay, now what I want to do is look at an example of the second type. Now, if you ever buy a Schomes outline, that Schomes they're written for every discipline that's ever been in STEM. And there's a really nice Shomes outline on advanced calculus. And they give a nice treatise of all types of improper integrals. They give the Fourier analysis. They talk about the gamma function, which is another integral type transform with which is the infinite limit of integration. What's nice about the Shomes outlines are they're like going to Wikipedia. You just get everything in one place, but it's in one bound book. And sometimes what students can do is they can go to Amazon and purchase the PDF, and you can have that in your computer and utilize like an ebook that we have for calculus. I've even thought about doing that before. I remember when I did a open books Cal 1 class, I've shown you this before. I used the Shomes outline in calculus. And so everybody had this book. And talk about voluminous, just problem after problem after problem. Calculus 2, Calculus 1, and even Calculus 3. But they found it to be difficult. I said, well, this is the old school. But I guess old school was maybe more challenging. But they are great reference objects. That is, you can put them in your personal library and you'll never throw them away. I've kept all my Sham outlines from even my undergraduate days. So that's kind of interesting, but not at all surprising. Now, the next type of example is where we have an infinite discontinuity. So let's look at this. Notice the limits are, as we say, proper. And we have X, again, we're going to throw in some more integration by parts. Like I said before, that's one of the most powerful techniques we've learned. Partial fractions, very powerful. Trig sub, very powerful. Even the Weierstrass, very powerful, but somewhat painful. Now, when we look at this and we think about this particular setup, X is fine, but we know that the natural log is certainly not defined at 0. It diverges to negative infinity. So when we look at this particular problem, we can't just ignore the fact in this particular case that there's an issue here. For instance, when we define the Riemann integral, we are basically saying that the integrand is defined on the interval of integration. That's huge. I mean, you know, we like to have bounded functions because we're thinking of maxima and minima depending on the integration theory that we use. So when we look at this, we're thinking, okay, think of a number line. And we have the 0 here, which we will be approaching from the right. And then, of course, we have the 1 here, which is no problem. Again, log of 1 is 0. It's continuous there, no issue. But we have the problem here. So basically, what we'd have to do is replace the integral with a limiting object of approaching 0 from the right. So again, what we're going to do is we're going to have our integral and we're going to have our limit, and we're going to operate on the integral. And then once we have a simplified form, we will pass to the limit. So this will be the limit. And again, I'll pick A here. We don't have any A in the integrand, so that's a safe letter. You could use alpha if you wanted to, it doesn't matter. So A approaches 0 from the right. And we have the integral. And now, of course, the lower limit becomes A. Remember, in the previous problem, A was approaching negative infinity. Now A is approaching 0 from the right. So you just have to check out the integrand and see, is this integrand continuous on 0 to 1? And when you figure out that it isn't, now, of course, this is at an endpoint, but it could also occur at a point that is intermediate between the lower and upper limit. So don't just assume that if the endpoints work, that everything's okay in the numbers in between. So you need to also check those. And that, again, is a harder problem because then you have to approach from two different sides, left and right. So now we have x ln x dx. So at this point, we can look at this as an integration by parts problem, compute the integral, and then pass to the limit. So let's go ahead and do that. So again, we'll use the informal nature now that you're professionals. The first time I go through it, I put through all the U's and the DU's and the DV's, and then you see that that's not really necessary. The techniques that I introduce will help you remember this, but you have to be respectful of the formula, that is, of the product rule, which obviously is the basis for this technique. So now, of course, we're going to differentiate ln of x because that's easy, and we're going to integrate x again because that's easy. So the derivative of ln of x is 1 over x, and the antiderivative here is x squared over 2. So just the same song and dance you did on your test. I was very impressed with the application of integration by parts on some of your papers. You followed my instructions, and now you have a very, very good technique in the toolbox, so to speak. So here we have a plus, and here we have a minus. So now we have the process of integration by parts. Now we can move back to the problem. So we have the limit as a approaches 0 from the right. And now we have 1/2 x squared ln of x. So 1/2 x squared ln x. So we're thinking if we do that one, that's going to be a L'Hopital because we're going to have to rig it. And then of course here we have minus. So we've got what? Minus the integral a to 1. And we've got, well, notice here the x absorbs into this x, so we just get 1/2 x dx. So application of integration by parts, move back to the limit. Now we need to operate on this and then apply the limiting process. And of course here, we evaluate from a to 1. Again, it's not an indefinite integral, so we can't just be sloppy. Now we'll apply the fundamental theorem and of course compute that integral. So we have limit as a approaches 0 from the right. And so now we apply 1, so we're going to get a 1/2 times ln of 1 minus 1/2 a squared ln of a. Of course, that term will be 0, but then we're going to have to operate on that with the limiting process. And then we have minus, we've got the 1/2, but then we'll have the a squared over 2, add 1, divide by the new power. So this will be 1/4, excuse me, x squared, and then a to 1. So very simple integrals, easy reduction here. So we have the limit as a approaches 0 from the right. Of course, this is 0. And now what we're going to do is we're going to notice, at least here, that as a approaches 0, this becomes negative infinity, but that's just 0, and that's 0 times infinity. That's indeterminate, but that's not 0. We don't know that. That's not like, you know, infinity times infinity, which is infinity, which is easy. So basically what we can do is run the a squared downstairs and produce another infinity to get the nice form for L'Hopital. So in this particular case, and this is what's important about this, we'll just say negative 1/2, and we'll say log a, and then just move this downstairs, a to the negative 2. So that's just like saying a squared is 1 over a squared, because it exactly is. And so now we'll be able to operate on that with L'Hopital. I'll say a little bit more about that. And then of course here we have minus 1/4, and substitute 1, we get 1 squared. And then we have what? Minus a squared. So let's go ahead and write all of this out. So this will give us equals the limit as a approaches 0 from the right. And let's just go ahead and operate on these. Let's use linearity and do them all separately so we can see what we have. So we've got what equals, so factor the -1/2. There's one limit, use linearity of the limit. And then we have, of course, the minus the limit as a approaches 0 from the right of 1/4, again, factoring the negative using linearity. And then, of course, here we have a negative times a negative. So that'll be plus 1/4 the limit as a approaches 0 from the right of a squared. Okay, so when you look at these particular problems here, once we get to this point and we want to clean it up a little bit, we can say, okay, well, the limit is linear, so we can apply the limit to each of these because that's just going to clean up our process. Now, these limits are easy. I mean, you can do those in your sleep, but now let me write the rest of the stuff in here that I left out and squeeze that in there. Now notice here, as a approaches 0 from the right, again, we get a negative infinity here. And of course, as a approaches 0 from the right, that's basically 1/0, which is infinity. So we get the so-called infinity over infinity syndrome. Plus or minus doesn't matter. This is indeterminate. And so now we can say when we compute this a limit, we can actually use L'Hopital because we have rigged the quote unquote infinity over infinity indeterminate form. And so now this will be, we say L'Hopital. So this is -1/2 limit as a approaches 0 from the right. Okay, the derivative of 1/a, or excuse me, limit of log a is 1/a. I go ahead of myself. The brain just thinks too fast. And then of course, the limit here will be, or the derivative here is -2a to the -3, just using the power rule. And now, of course, the limit -1/4, that's just what -1/4, that's a constant. And then, of course, the limit here, if a is approaching 0, a squared certainly approaches 0. So that's plus 1/4 times 0, which of course is 0. And now let's clean this up a little bit. We have -1/2 the limit as a approaches 0 from the right. So now we can just take this upstairs. So this will be a to the third over -2a. So now we have -1/4. Now notice this will be -1/2 times the limit as a approaches 0 from the right. And of course, now this will give us a squared over -2 -1/4. And we'll finish up here. We'll just move the calculation up here. So factor the negative. So that'll be +1/4 limit as a approaches 0 from the right, again, of a squared, which we know is 0. So we get 1/4 times a 0 minus a 1/4, which is -1/4. Now, when you think about the concept here and basically what we're doing in this particular problem, it's very important when you think about this. What we want to do is make the problem as simple as we can. That is, work it out using the techniques that we learned in Calculus 1 and so far in Calculus 2. And then here, of course, I'm putting in all the steps because it's important. This is an excellent example of L'Hopital with the improper integral definition. So when we get to this point, we apply L'Hopital. And what I want to show you here is that you want to, again, just like you're in Calculus 1, simplify this. That is, put it in a form where you can pass to the limit. So what does this equal? Well, the a is absorbed, and then of course we have a -1/2 and a -1/2 here. So that gives us a 1/4. And now we have a form where we can actually pass to the limit. Again, remember, when we are looking at this, we have to write this in a form that allows us to pass to the limit. That is, when you do calculus 1, the temptation is always to jump to the limit too soon, and then you're actually not seeing what's going on. It's allowing the algebra to relax to the point that we get a function that we can easily understand. And so now what we're seeing is that with the application of L'Hopital, this limit is actually 0. And so now we see that the improper integral converges. So this implies improper integral converges. That's what I like about the improper, because then you see a use of L'Hopital that's just outside of the academic process. Again, apply the integration by parts, rig the infinity over infinity, take your derivatives, power rule, derivative of the logarithm, simplify, pass to the limit. And again, we have what we call a nice improper integral. Now, remember with the second type, it's a little less apparent. That is, you have an integrand that has an infinite discontinuity on this interval of integration. And so what I normally have my students do is just sketch the interval and basically symbolize the limiting process. What do you have to do in this case to rewrite this so that it is a limit of a proper integral? Okay, improper limit of a proper integral is using the definition. Okay, so let's try another one. Now, one thing I found is that when it comes to doing the second type here, it's better to practice and then throw in some integration techniques that you just learned to give you extra practice. Now, here's a nice example of that. So we have the integral 3 to 5 of dx. And of course, this is going to be a trig sub. Of course, it could be an inverse hyperbolic, but I've taught you the trig sub, so we'll do that. Clearly, when you're using a integral table, like on the next test, I'll say use an integral table to compute this integral, okay? If I say that, I want you to use an integral table and show me the integral formula you're using, like I say with the formulas from our appendix. Now, if I don't say use an integral table, you can either use a technique I've taught you, or if we have proven the formula in lecture, you have that at your disposal. So like I say, most of you decided to integrate secant cubed when we had already proven that formula in lecture, which you could have used. And when you look at the solutions, like I said before, I wrote that in. So that you always have at your disposal. So again, if it doesn't say use an integral table, you either can use something we proved in lecture, or you work it out with the technique that you have learned. And I know you all like the miscellaneous. It just seems to be something everybody gravitates to, which is fine. It's a major technique. Now, when we look at this, and again, we think of the same thing as we had before, again, introducing this in a way that's a little bit less tedious. Again, as you look at the lecture notes on Blackboard, there's some other examples that you can look through too, just to give you some additional practice. But notice here at 3, we have a problem here. We get the infinite discontinuity. So again, when we look at this, we can think 3, approach from the right, no problem at 5. 5 is well defined. We've got this radical in the denominator. We don't want to divide by 0. So again, we can use a letter in this particular case that's not being used. We'll just use A again. Again, use a letter that's not already being used here. We'll be fine, whichever letter you like. So a approaches 3 from the right of the integral a to 5 dx square root x squared minus 9. Now, of course, with this problem, you know, I've taught you trig sub, and you probably did the inverse hyperbolic forms in Calculus 1. But I want to take an opportunity to use the trig sub again, because that's something you learned last week, and just practice with it. So we'll just operate on this. Notice this is the u squared minus a squared, which is the secant substitution. So in this particular case, we're it's funny, we always call the a, we call that the a. So let me do this. Let me do this. Let me change this. Let's just call this alpha, because when I think about how we do these forms, that's always the a squared. So let me use alpha instead. So of course I got to change this to alpha. Sorry. I mean, I'm thinking, we're not using any letters so far, but then if I'm going to do trig sub, we need to change that. So let's use alpha. So that'll work. So now notice here we have u equals x and the a equals 3. So we can say, in this case, x equals, in this case, 3 secant theta. And now we're going to get a nice triangle here, so that's going to be even better. So at this particular point, when we think about this and changing the limits, so to speak, let's just look at this. So in this case, dx will be 3 secant theta tangent theta d theta. And then, of course, if we apply this, we've got what? Theta will be the inverse secant. And of course, here we just divide by 3 of x over 3. So now we're thinking, okay, so this alpha is approaching 3 here. So what is it going to approach in the new limit? So let's just kind of check that out. So theta of 5, well, that's just going to be a kind of unfortunate number. We can draw a triangle with that. That'll just be inverse secant, excuse me, of 5 over 3. And we can draw a triangle with that. So let's do it. So here we have theta, and then we have hypotenuse over adjacent, right? So that's a Pythagorean triple. Of course, that's a 4 right there. So that's a nice triangle. And then, of course, we're approaching 3. So we just say theta of 3 will be inverse secant. Of course, 3 over 3 is 1, but we know the inverse secant of 1 is just 0. And then lastly, we just need to know what this is. So now we can just say, of course, you can memorize these. So now we're going to have the 9. So we're going to have the square root of 9, and we'll have secant squared theta minus 1 to the 1/2. But that just gives us 3 tangent squared theta to the 1/2. But now, of course, we're in the right branch of the secant function between outputs 0, pi over 2. And so this we can take the positive with the absolute value. So this is absolute value of tangent. Of course, we just choose the positive when we're doing an indefinite for ease. And this will just be 3 tangent. So what I wanted to do is just take some time to go back over a trig sub where we have limits and just review that, because that's always good to do. It's a little busy. It's not overly hard, but you do have to think about the notation. So now we can say, what does this equal? So now we'll have the limit. In this case, now alpha is going to get replaced with theta. It's the new, so theta is going to approach now 0 from the right. And then we'll have, in this case, theta to 5. So what we're seeing here and what we're noticing in this particular case is when we think about what we're doing and we think about changing the limits, it does impact how we define all of these. So now we've got this alpha approaching 3 from the right. We make a substitution, we change the limits. So now we've got a new variable, and now dx is what? 3 secant theta tangent theta d theta, and then of course the square root is 3 tangent theta. And so you're thinking, why don't we just use the inverse hyperbolic? But I want you to practice with this. Now notice, of course, the 3 and the tangent absorb. So this gives us the limit as theta approaches 0 from the right. Now, of course, of theta to 5 of secant theta d theta. And of course, that's just a Cal-1 integral. So the integration method trig sub is very, very useful. And again, what's nice about trig sub? You don't have to remember a whole lot. It's all based on right triangles. So if you can remember the convenient substitution, you can always work it out. But of course, integral tables are useful. Integral tables are very useful, especially in physics and engineering when you need a quick answer. So again, just look at this as an opportunity to practice our newfound technique, trig sub. So now let's move everything down here where I have a little bit more space. So this will be the limit as theta approaches 0 from the right. And now the integral is our famous natural log of secant theta plus tangent theta, right? So we have the natural log of secant theta plus tangent theta. Oh, and of course here, you all are thinking the new limit, ding, the new limit here, that's why we write everything down. The new limit here is inverse secant of 5/3, obviously. I bothered to change the other. So let's make sure I put in the new limit. That's what's so nice about math. You've got it right here, and it always guides you. That's why I like to see your work, and I have to see it. I go through every line of what you do, and I'm pleased that there's improvement. So if you write your work, I can see. And then, of course, as I teach, I use my work to guide to the next level, just like any mathematician would do or any math student would do. And so now we've got what? Tangent of theta, absolute value. Well, I'll make it a little bit larger than that. And then we'll do, what do we have? Theta, and we have inverse secant of 5/3. And of course, we have our triangle here to help us out. So let's apply the fundamental theorem of calculus. So we have the limit as theta approaches 0 from the right. So we have natural log. So let's apply this. So we have secant of inverse secant, I'll write it out, of 5/3. So note, these will just absorb, plus tangent of, in this case, inverse secant of 5/3. So we get to use, again, this is just the theta, so we use the triangle. That will not be difficult. Now we have minus natural log. Now we've got theta. So the key here, and what's interesting about this is that I guess again with the notation here, I could still use the other letter, because now we're saying that as we write this out, theta is just replaced with theta, and we let theta pass to 0. So that'll work. How interesting. So now we have the limit as theta approaches 0 from the right. And now we can do all of these. This will be natural log. Of course, that'll just be 5/3. And then tangent of alpha, or in this case, theta, is just 4/3, opposite over adjacent. So just using the right triangle. Then we have minus natural log of secant theta plus tangent theta, absolute value. So now when we look at this and we think about, okay, what's left here and what do we have to do? So let's pass to the limit. That's a constant. So this will be, that limit is what it is. So this is natural log of what? 5 plus 4, that's 9/3. Minus, now we can use the linearity of the log and the absolute value. So this will be natural log of the absolute value, and we can pass the limit inside. Theta approaches 0 from the right of secant theta plus tangent theta. So of course now that's log of 3, and this will be minus log of the absolute value. Okay, now was theta approaches 0, that's secant of 0 plus tangent of 0 by the limiting process. So this is log of 3, and of course this is just equal to 1, and this is equal to 0. So we get log 3 minus log of the absolute value of 1. Of course, that's 0. So we get log 3. I'm trying to do ones that actually converge. And what's important here is that you're thinking, I was a little bit, casual here. I could still use the same letter. Again, we're allowing, you're thinking, I've got the variable and these are coinciding. I still could have stuck with that, but it's your choice. It's flexible enough that we can get by with that. But if you would prefer to stay with another letter, you certainly can. We've got a fixed limit here, and here we've got, again, it works well. I made a comment about that. Flexibility in notation is fine in calculus, and I'm not going to be too picky about it. But technically, if you just wanted to stick with another letter here, that would be fine. But we see there's no issue because when we actually integrate, we can let theta pass to 0 from the right, and we get exactly what we need. So now what we're seeing here is that with the second type of improper integral, we continue to use the techniques that we've learned previous to this, but now we simply apply the limit. So this is like the convergence of integration techniques from calculus 2 and the limit techniques from calculus 1. Put them together and we have a new type of problem. Now, the beauty of this and what I like about the improper integrals is that they make you better at what has come before because you get to practice everything, and the problems tend to be rather long. This is like doing the Weierstrass substitution. Once you do the definite indefinite integral, then you change the limits, then you work out the limit. The limiting process must be done step by step. You can't just jump to the limit. You have to reduce what you're doing and then move to the limit in a way that makes sense. And what I love about this problem is that it's kind of busy. So it makes you think about all the different techniques that we've been doing. So what do we say now? We say improper. This implies improper integral converges. Improper integral converges. One thing that's nice about doing analysis is that you will never be at a loss for problems to work on. I enjoy doing Fourier analysis. I love abstraction of number theory, but the Fourier analysis and working with transforms to me is fascinating. And so you never have to worry about running out of problems to work on. They're all over the place. I mean, it's just like finish a problem, there are a million more to work on. Now what I want to do, there's several examples of nice problems, but I want to give you a couple of techniques that are kind of useful. It's like if we're integrating e to the negative x from 0 to infinity, as we saw in the first problem with the integration by parts, we're pretty much comfortable with the fact that that's a decaying function. And pretty much intuitively, we think, yeah, that's gonna converge. So basically, when we have infinite limits of integration, like maybe say 0 to infinity or 1 to infinity, we're thinking of, okay, once we apply the anti-differentiation process, are we going to have something that will converge? That is, clearly, if the actual antiderivative becomes infinite as x approaches infinity, then that's going to blow up. And so, or that's obviously a divergent case. So our intuition is actually really important when we think about transform methods. So as a method to introduce that, I want to show you about the P integral. This will also turn into the P series when we talk about infinite series. So there'll be a interchange of ideas between the improper integral with the integral test for infinite series. So it's like we're actually doing something now that's going to pay off handsomely in the next chapter. And so this theorem we call the P integral. So it's actually good to have a few items that we know about that we can always utilize when we're doing problems. And it looks like this. It's improper, 1 to infinity of 1 over x to the p dx. So this particular integral, you're thinking, oh, that's just a power function, Professor Ron. I think that's something we have a little bit of intuition about. But when you look at this actually converges, and we actually know what its value is. That is, this is actually 1 over p minus 1 when p is greater than 1. Now, intuitively, that makes sense because when you think about the anti-differentiation process, you want to keep the variable in the denominator because as x would pass to infinity, that particular term would converge, okay? It would approach 0. So intuitively, you're thinking, oh, you could rig some problems with the infinite limit of integration as long as after you anti-differentiated, the x's were removed to the denominator. So the key here is that not all problems, I mean, when we think about this last problem, this was a lot of work and intuition would not maybe be as clear here, okay? But in this case, it will be. So let's just see why this is true. This is a really easy proof. Why? Now, again, since we've got this P integral and we have a value, it's kind of like the geometric series. The geometric series, we'll find out, is just a blessing. It's like without it, we would really be in a tough place. As I've said before, a visiting complex analyst at A&M when I was in grad school, I said, well, what would we do without this? This was in a complex analysis course. She says, well, we'd have to work a lot harder. I said, well, I don't know. We depend on it so much. It's like, what would we do? It's kind of like thinking about how would we be doing trig sub and things like that if we didn't have the Pythagorean theorem? I mean, I guess we don't need to be negative. We have it, but you think about removing major theoretical constructs from our vocabulary and then think, well, how would we do it? So mathematics has evolved in a way so that things that are really useful stick around. Things that are not as useful, it's not like We don't care about them, but we don't use them as much. So we'll always be stuck with the Pythagorean theorem and Euclid's geometry. And of course, we'll be stuck with the fundamental theorem of calculus. So first, we're thinking, okay, what's the step here? Well, let's just think about this. Let's take P equal to 1. How do we integrate a power function? Okay, well, we add 1 and divide by the new power, right? But we can't do that when P equals 1. That's log. That's natural log. So let's look at that case and then look at the power rule. So we have 2 steps in this proof. So P equal 1. So now we have the integral 1 to infinity 1 over x dx. Don't we wish all the integrals were this easy? So P is 1. So now we apply the definition. The limit as P approaches infinity, we'll say B, sorry, B. So this will be 1 to B. The B's look like the P's, sorry. And we have 1 over x dx. So now we apply the antiderivative. So this is the limit as B approaches infinity. So this will be of the natural log of the absolute value of x, evaluated from 1 to B. So when it's less busy, it's kind of nice. That's why I said this was a little bit easier. We've done some limiting examples that required a lot of work and a lot of manipulation, where this is very straightforward and very clean. But again, it makes us appreciate these problems. So now we have the limit as B approaches infinity. Now we have apply the B, so we have the natural log of the absolute value of B, and then minus the natural log of 1, absolute value of 1. Well, of course, that's just 0. So we have the limit as B approaches infinity of the natural log of B in absolute value. But of course, the log function is increasing. And as B increases, so does the natural log function. We learned that in calculus 1. So this is infinity. So the thing is, just because you're doing an improper integral doesn't mean it converges. It can diverge. So we just say diverges. So nothing here. We do not get any results when P is equal to 1. So this is the first case that I've shown you where we have a divergent improper integral. So, okay, but this theorem is saying that if P is bigger than 1, we should get a value and it should converge, and we actually know what it is. So let's see if we can prove that. Now we'll say P not equal to 1. Okay, and this is where we'll look at the antiderivative and then say, when would we get convergence? So we'd have to look at where x was its disposition relative to the numerator and denominator. So now we have the integral 1 to infinity of 1 over x to the P dx. Now we apply the definition. This is the limit as B approaches infinity. Now, if you will, we'll say 1 to B. And just to make it a little bit easier to anti-differentiate, we'll just say x to the negative P. Add 1, divide by the new power type thing. It's always nicer when we do that. And of course, now we apply the fundamental theorem. So this will be the limit as B approaches infinity. So add 1, divide by the new power. So this will be x to the minus P plus 1 divided by the new power minus P plus 1. And so this will be 1 to B. So now, if you will, let's just go ahead and rework this in a way that's nice. We can go ahead and factor this constant downstairs. So this will be 1 divided by, and we'll just say 1 minus P, 1 minus P. And we have the limit as B approaches infinity of x to the negative p plus 1 evaluated from 1 to b. And so now we'll apply the fundamental theorem. So we have 1 over 1 minus p limit as b approaches infinity. So we replace the x with b. So b to the minus p plus 1. And now replace x with 1. So minus 1 to the negative p plus 1. Of course, 1 to any power is 1, so that's simple. So this gives us 1 over 1 minus p. And now as we pass to the limit, we look at this. First, let's go ahead and simplify it a little bit, and then we'll use our logic. So this is b to the negative p plus 1. And of course, this is just minus 1. Now, if this is going to converge, it will converge to 0. So when will that happen? Well, this is going to happen when negative p plus 1 is less than 0. That is, it moves the b into the denominator where the b can grow infinitely relative to the numerator of 1 and converge to 0. So now this will be 1 over 1 minus p times 0 minus 1 if and only if minus p plus 1 is less than 0. If and only if, now we just take the p over, p is greater than 1. But what does this equal? Well, this is 1 over 1 minus p times a negative 1. So that just flips this, and this gives us 1 over p minus 1. So indeed, if we move the variable into the denominator, then we can get convergence, because then we just have 1 over a power function where x, or in this case b, passes to infinity, and that will give us a 0 limit. So this is where we have to exercise convergence properties from calculus 1. And that's where the transform methods are very powerful. You say, well, okay, I've got all these letters running around. What's the best I can hope for? Well, this will converge to 0. Otherwise, it diverges to infinity. So of course, if minus b plus 1 were greater than 0, then this would just blow up. B gets larger, and then b to a positive power gets bigger and bigger and bigger. So the key here is just exercising your understanding of limits at infinity from calculus 1. So indeed, when you have this improper integral, the value is 1 over p minus 1. That is, converges if and only if p is greater than 1, which we have here. So this we put in our back pocket. This is a very, very useful result. And then when we get to the integral test with infinite series, we're going to find that this will give us another leg up with infinite series, in the sense that it'll give us a whole basket full of convergent series. So we are grateful to relatively straightforward results that give us plenty to work with. You know, we think about differentiable functions, so easy to work with. We think about antiderivatives, not always so easy to work with because of that blasted constant that makes everything difficult. I mean, when you think about it, you know, if I've heard professors say many times, especially when I was a younger kid at Carolina, you know, I would tutor students and they'd say, oh, my professor said, if I don't get this anti-differentiation, I'm sunk. And I said, well, what your professor's saying is that you have to understand the connection between the derivative and the antiderivative, but the process of anti-differentiation is more complicated because of the mean value theorem. You have to work harder. And so they're thinking it's gonna have to eventually click. And when it does click, you're like, you know, it's a downhill. I mean, there are a few bumps in the road, but it's a downhill voyage after that. And I had to reassure the student. I said, you'll get it. I said, you'll put in the time to get it. We always love the aha moments, right? Now, there's one other result before I just give you the transform, which can be very useful. It's a comparison theorem, and this is what we're going to talk about with infinite series. And so I wanted to give you the analogous result with improper integrals. So when we get to infinite series, you'll be like, oh, that's the same thing. So for instance, this is called the comparison test. So it's a bit restrictive, but it has to do with positive functions, like we're going to talk about positive term series. So for instance, if we have the following inequality, say we've got these non-negative functions that their outputs are 0 or greater, they're non-negative, and we have this inequality for x living, say, some fixed number a to infinity, where a is fixed. A element of R is fixed, a constant. So it's kind of like we're doing the Riemann integral result, where we'd have an inequality where if we did the integral here, it would have to be an upper bound for the integral here on a particular interval a to b. That is, the integral would preserve the inequality if we had this kind of a construct. So again, it's one of those things where we're starting to see ideas that parallel what we've seen before. So if this is the case, we can look at the following. So here's what's interesting. So here are the two results, and we'll prove these with the infinite series. These are logically equivalent. So here's something that's interesting. And let me just make sure that let's see here. Yeah, here we go. So if we look at the improper integral of f from a to infinity, f of x dx, and when I say the improper integral, ladies and gentlemen, converges, I'm going to say it's less than infinity. So that means this is a finite number. If this converges, and we basically say when this is true, I'll use this notation in infinite series, we'll say converges. If this converges, and of course, f is an upper bound for g, then this would imply that the improper integral of g of x dx would also converge. We'll say it's also less than infinity, converges. We'll actually, and you could prove this now, but we'll actually prove this with infinite series. I'll give you a break at this point, but what we're going to do is apply this idea to the infinite series and get the same result. And then if you look at the contrapositive of this, suppose that the integral here diverges. So we're going to say that a to infinity of g of x dx is actually infinity. And we'll say it equivalently, we'll say it diverges. Well, if this is a lower bound for the f, this would force this integral of f to also diverge, again, preserving the inequality. So this would imply that the integral a to infinity of f of x dx would also diverge. So this is a very important construct in the sense that infinite series behave the same way. If you have the analogous positive term series, it will react this way. And so we're going to use the p integral and the p series to have nice ways to compare functions. That is, when you think about this particular result, we can actually solve a problem. That is, here's a use of this result, a very simple result. So the idea is, if you know something about one improper integral like you have here, you can make a conclusion about the other without doing additional work, okay? Or, once you have a basic inequality. So here's an example. Look at this. 0 to infinity of 1 divided by e to the x plus x dx. Now, we know that 1 over e to the x or e to the negative x, that's one of those integrals that's going to converge because of the negative. That is the 1 over e to the b, remember as b passes to infinity, we've already seen that in action. That's a nice convergent improper integral that we saw in that first example that we did. It was kind of off to itself, but we see that that gives us a nice example of a convergent improper integral. So now here's what we observe. Let's tie this into the discussion. Observe. So here we've got 0 less than e to the x. Again, notice here, x lives here. And this is less than or equal to e to the x plus x. If we just tack on an x, we just get a simple upper bound because x is non-negative. So these are all positive quantities here. So now we can reciprocate. So now this will flip. So we'll have 1 over e to the x plus x, flip the inequality, will be less than or equal to 1 over e to the x. And these are clearly positive. So this is the beauty of this argument. And sometimes students say, well, Professor Ryan, I don't like these inequalities. I'm like, but here's the thing. We don't try to envision the inequality without building it. Like here, we start with something simple. This is a college algebra technique, which I teach. When I occasionally teach college algebra, I teach it. I'll say, okay, kids, we have two quantities that are related by an inequality. They're both positive or they're both negative. Then we can reciprocate. And they enjoy it because we just do all these little problems to create new inequalities. And I'll say, when you get to calculus, this will be very useful. Now, of course, most of them forget it by then, but I have had a few students, especially in the honors courses, that say, I remember when you talked about this. I said, good, bring it back. So now again, observe, and this is what we've already looked at least in one form, the integral from 0 to infinity, e to the negative x. This converges. That's a real simple result that we actually showed in conjunction with the problem we did in the first at the first of the lecture. This actually converges. So now we're right up here. We've got the upper function, so we can think of this, ladies and gentlemen, as f of x, and we can think of this as g of x. So now, well, sorry, I flipped them around. Let me go down to the last inequality. Math is so rewarding, right? So here's the f of x, this inequality, and here's the g of x. So here we've got this, and here we have this. So now you see that this integral converges as we have here, and therefore the lower bound function upon integrating will give a convergent integral. So if this works, this will imply that the given integral, which is the integral of g, now converges by the comparison test. So we use our inequality to effect this argument. Converges by, and then of course we'll be lazy and say comparison test shorthand. So the key here, again, this was the original inequality to set up to reciprocate. So that these are not the g and the f. The g and the f would be in the second inequality, as you see. And so then you basically have the inequality from the hypothesis, and then you have a result that you are aware of and use this result to affect this result. So again, it's not always important that we know the actual value of the improper integral. We just need to know that it converges. And then, of course, we can always utilize techniques to get a decent approximation of the improper integral using Simpson's rule or something that you learned, an approximation technique from what is it, Calculus 1. So just like with infinite series, many times we'll be able to say, okay, this infinite series converges. And then if we need to get a relatively good approximation, we'll be able to do it. The thing is as engineers or future engineers or mathematicians or computer scientists, you will need an approximation that is reliable. And so that's why you have to work with exact computation. So once you start the method of giving a good Google approximation, you're starting with good ideas. You're not starting with flawed ideas. Like I try to convince my pre-cal kids, it's like, okay, you've been approximating all through this interest problem, and now you're worried or you don't understand why your result is flawed. I said, you do exact computation, and then if you need to approximate, you start with good items, okay? And that will never, ever change. If you've had any statistics, and of course, the decimal approximation of the computer can be a nightmare. You get results that don't even make sense if you don't keep track of what you're doing. Now, what I want to do is say just a little bit about the Laplace transform. Now, it's related to the Fourier transform. And I've got some nice examples here about smoothing out functions and things that I may share with you eventually. But I want to just give you something relatively straightforward now so you can say, oh, okay, I get it, Professor Ron. This will be a nice example that we can do. And let me give you the Fourier and the Laplace just so you have them. So I'll just say two important transforms. And these are based on the improper integral like the P integral, not the infinite discontinuity, but the infinite limit of integration. Now the Laplace, and this is, again, for the Laplace transform, we'll just use a big F. S will be a parameter. And of course, F will need to be of exponential order, but you're going to learn about that in differential equations. This was defined as 0 to infinity, f of t, e to the negative st dt. Okay, so you can see that computation here would involve integration by parts, and that's where it's nice to have some of the integral tables, or at least an understanding of integration by parts. And then the Fourier, and these are related, we'll just use g of w. W is a real variable, real parameter, but it runs from negative infinity to positive infinity, f of t, but then we have the complex exponential, which is Euler's theorem. So we have e to the I omega t. But the nice thing about the complex exponential is that it integrates and differentiates e to the z, where z is a complex number. It integrates just like the real, so there's no new calculus to learn. So I'll just say here where I is the square root of -1. Now, I've got two examples here, and what I want to do, let me go ahead and just run through these for a specific example. So here's the first one, and there's a smoothing one that I'll do later when I have time. It's a little bit more complicated, and you all aren't ready for that, but you could do this. So here's an example. We'll take f of t, will be the following function. It will be 0 where t is less than 0, and it's going to be e to the negative t when t is greater than or equal to 0. So when you think about this, let's just draw it. I mean, you know, we did take college algebra, right? So So at 0, you just get 1. That's the nice decreasing function. So it looks something like this. Like that. And then of course over here, it's just 0 and then open, right? So this is f of t, the decreasing exponential, but it zeroes out here. So this is 1. So this is where we use our college algebra. You know, I always told my honors kids, I said, you learned everything you need to know in college algebra, even though that wasn't true. That was the beginning of it. And they'd always laugh and for whatever, you know. So now notice if we can apply this, but here, if we would apply this particular transform for the negative infinity to 0, the integrand would just collapse to 0. So that would show you that there is a connection here between the two transforms. Of course, there's much more to it than that, but let's go ahead and work on it. So let's do f of s. Let's do the Laplace. So we'll have 0 to infinity. And now, of course, for 0 to infinity here, we have e to the negative t. So f of t, e to the negative t. So e to the negative t, and then e to the minus st dt. So now let's apply the definition. So this will be the limit as b approaches infinity. Now, sometimes professors just do infinity as a limit and don't do the b and all these formalism that I'm doing. I'm okay with that, but not the first time through. When you get to physics and all, you can be a little bit more flexible, but now I need to see this technique. So we've got what the limit 0 to b, and let's go ahead and factor these exponentials. So this will be e to the negative t, and that would be just what? A 1 plus s, right? Now, what's interesting about this is that this is going to allow us to use our techniques that we've been learning today. So now what we see using the laws of exponents, we can rewrite this product this way. So we have an integral that we can do. So now we'll apply the integration process. Of course, this will just be negative 1 over 1 plus s. That's the k, so to speak. So we get negative 1 over 1 plus s. Just go ahead and factor that using the limiting linearity. And so we have e to the negative t times 1 plus s evaluated. Again, this is part of the antiderivative, which I just removed by linearity, and we evaluate from 0 to b. So this is negative 1 over 1 plus s, and then we have the limit as b approaches infinity. So now we substitute b for t, so we get e to the negative b times 1 plus s minus, of course, now we substitute 0, so we get just e to the 0. Now, in the limit, we do just like we did for the p integral. This will work as long as the 1 plus s is positive, because that will drive the negative down, and this will converge to 0. So now we say this equals, just like we did with the p integral, 1 plus s, and of course this will be 0 minus 1 if and only if 1 plus s is positive. Again, that will drive this into the denominator, and then of course we'll get the convergence to 0. But then of course this is just equal to negative 1 over 1 plus s times the negative 1, which is just 1 divided by s plus 1. And then of course now this says s, well, of course this just says s is greater than negative 1. That's another way of rewriting that. So if we do the transform of f of t, we get 1 divided by s plus 1. That's the Laplace transform of f of t. Now, what is good about this? Well, that's a rational function. And so you're thinking, oh, wow. We'll put all this stuff together and we'll do partial fraction decomposition until we're crazy. So the idea is calculus 2 is such a bedrock of all of this because it requires that you use all of these techniques. And let me tell you, the properties of these transforms will keep you busy. And then, of course, your application of partial fraction decomposition will make your head spin, but it'll work. So the transform methods are not simple, but they are certainly very, very useful. Now let's look at the remaining part. So now let's do, again, we got the same function, but let's do the Fourier. So now we'll have g of omega. We'll just change the letter because that's what Fourier liked. And so now this will give us, again, remember, we'll have negative infinity to 0, but in that part, the f of t, remember the f of t, let me just write it down here so you can remember what it is. It's 0 for t less than 0 and e to the negative t for t greater than or equal to 0. And so when we do the Fourier transform, we have e to the negative I omega t dt, that'll just be 0, plus 0 to infinity, e to the negative t, e to the negative I omega t dt. So now, of course, this is just 0. So now we can apply the definition of improper integral here. So we'll say the limit as b approaches infinity, 0 to b, and do the factoring process. So we have e to the negative t, and this will be 1 plus omega times I. I'll do the I first, I omega. So it looks just like the last one. So now when you look at this and you think, okay, what's the next step? We'll apply the anti-differentiation. It'll be the same. We'll just get negative 1 over 1 plus I omega and factor it like we did before. So it's the same computation, but I just want you to see the difference with the imaginary unit. It's kind of nifty. And you see the connection between the two transforms. So now we have e to the negative t, 1 plus I omega, 0 to b. So we have negative 1 plus I omega, limit as b approaches infinity. So we'll replace again t with b. So we get e to the negative, in this case, t, 1 plus I omega. Now, what's interesting about this and what's very important is that this is a simpler calculation. And so let's just, wait a second. Let me just go ahead and substitute. Sorry, I didn't do that. B. And then we have minus E, and then of course to the 0. Now notice, and this is important, the complex number field again is not ordered. And so this is not going to cause us any issue here. And this is always, at least in the context of this is the positive part, and this has no impact because the complex field is not ordered. So this will work without any further restriction. So this will just give us negative 1. This will converge to 0, 1 plus I omega times 0 minus 1, which will give us 1 over 1 plus I omega. So there's the Fourier transform. So the key here, if we compare the two, notice here, these are real. 1 plus s these are real numbers here. When we get to here, we're already fixed because this is not going to have any impact. This is the I omega, and it's going to be fine. That's a complex number. It's not, we don't have the ordering properties that we have. And again, one thing that's going to be interesting here, this is going to be Euler's theorem that you're going to use quite often in differential equations, which looks like this. E to the I, we'll just say theta, and that's what's bound up in all of this. Well, no, I'll just go ahead and I'll go ahead and write what we have from the transform, what this actually is. E to the negative I omega t is actually, in this case, I'll write it this way, E to the I negative omega t. This is Euler's theorem, so this will be cosine of negative omega t plus I times sine of negative omega t. And of course, the cosine is even, so this is cosine omega t minus, this is odds, so the negative factors, sine omega t. So there's more work trigonometrically going on with the Fourier analysis. But the beauty here is that we always have to, at least with the transform methods, take into account how we're actually working through these in terms of a convergence aspect. Here, what we're seeing is that there's more built-in trigonometry due to Euler's theorem, and this is something you'll be able to actually justify using infinite series. So what I wanted to show you is that what remains in your future is a lot of more complex mathematics, but like I say, it's very doable. That when you work with the Laplace and the Fourier, you learn their properties so that you can do algebraic manipulations to work the problem forward, get to a point where now you can take it back with the inverse Laplace transform and solve your problem. So the key is this: you're thinking, I don't need these transform methods if I've got nice functions. I'd be wasting my time. If I already got nice functions, I don't need to transform them. But the idea, if you think about what we've done here, and where's my picture? Yeah. If you look here, this is not a nice function, is it? It's got a gap in it. It's discontinuous. So when you do this, you smooth it out. This is nice and smooth as long as we stay away from -1. I mean, it's an improvement. So the key here, and another example that I had here is we could actually take a theorem or a point that a function that has a corner in it and then smooth it out. So these transform methods are how you deal with, like, if you have an input that's like infinite, like every second, that's like a sledgehammer. Or if you have a step function where the signal's on, then it's off. The signal's on, then it's off. That is a horribly unfortunate function. You want to smooth out these functions. You want to make them easier to work with. And that's what the transform method does. So this is not a useless construct. So I just want you to be aware of what you do with improper integrals, and you should look forward to it. All of you future electrical engineers, you will be doing this. When I was in grad school, all the electrical engineers in grad school came to our math classes to take mathematics, and they were an interesting group of people. They didn't like to study like we did, but I certainly respected their interest in the mathematics because they obviously needed it. But okay, so this is the end of chapter 8. Okay, we did the Laplace, we did the, the L'Hopital, we did the improper integrals, and we did the Weierstrass and all those interesting techniques. Now, the next meeting that we have after your break will be sequences and series. And so we're going to go into the realm of dealing with discrete things, at least in the sense of sequences and infinite series, and then apply the calculus to it and see how that mix of calculus that we've already learned meshes with the sequences in the infinite series so that you can do what? So that you can do series solutions in differential equations. So you need to know about convergence of series so you can solve certain types of different, and it is a beautiful, beautiful theory. But it's kind of like trying to do calculus without trigonometry. You have to learn that first. So I'll have a session today, and of course I'll have several sessions tomorrow. I've got to spend some time getting my students' tests for pre-calculus ready today so they can have a test before spring break. But I wish you well with your spring break. Get your work done, get your quizzes done, and stay caught up. And then, of course, over spring break, you can rest a little, but take the time to go back through the test solutions, take the time to go back and make sure that you clean up everything that we've already done. If you are still struggling with concepts, take some time to work through them. Go back through my lectures or take the practice test or the test you've just done and work through them and use valid techniques that will push you to the next level. Again, the class is not going to get any harder. It'll stay at the same level, but it will be interesting topics that I think you'll like a lot. And then, of course, once we finish with chapter 9, we'll do a little bit with the polar coordinates and the calculus of polar coordinates and parametric equations. So that'll be a fun way to end the class. So I appreciate your attendance today. Sorry for going over. I'm long-winded, but that's certainly nothing new. But I wish you well with the rest of your week as you complete your test and have a pleasant break. And again, if I see you at the office hours, certainly come by and ask your questions. If not, enjoy your time off. Have a good one.